morning to everyone.
Good morning, Dr.
Good morning.
Good morning, Doctor.
Me. Okay, we are going to start our class, right? But in a few minutes, I guess our friends are coming in, right, from time to time. So bear with us lah for some few minutes. Okay, now before I start, today we are supposed to start chapter 3. Okay. Now you have submitted all have submitted your quiz number 2. So I'll try to grade it as soon as possible. For assignment 2, it is due this Wednesday. Of course, you can submit earlier. Meanwhile, I actually wanted to share something about your chapter 2 because I realized I forgot to show you an Excel file regarding the best section. Let us take a look at it. All right. Okay, remember last time? Okay. Remember last time in our chapter 2, I talk about the best hydraulic section, right? Why we would say, why do we need to find the dimension when we set dP over dy equals to 0? That means we are having P minimum. Of course, when P minimum is the best section because the the cost to construct the channel would be minimum, as well as the channel, including the channel lining lah, basically. Okay. Now let's look at this. This Excel file actually shows the variation of P with respect of Y. I'm going to increase a bit. Right now, this is actually a rectangular. I'm considering the rectangular channel, which is actually in this chapter, in your chapter 2. I'm going to show the whole screen, which is easier lah. All right, my entire screen. Share, okay. Now, which is this guy here? All right. I should delete this. Okay, I've already showed this in your chapter 2. I said let's look at an example of rectangular section with flow area of 4.5 meters squared. That means this flow area is fixed, but the width of the channel or the depth of the channel is not fixed. So we wanted to find the most efficient size of the channel. So with this 4.5 meters squared, okay, we know that we are going to have such an area to cater, for example, to cater for certain discharge. So what we have here is no, this is different file. Okay, now so we have area of 4.5. So I would try, let's say I would try the rectangular channel width of I could have 0.5 meter with 1 meter, all right, 2 meter or so on. But this is at interval of 0.5 meter lah. I could have it 1 point at every 0.1 0.2 interval. Is up to you lah. So what I'm going to show here is actually an interval of 0.5 meter. Now if I have 0.5 meter, to make sure that the flow area maintain or stay constant at 4.5, what I have to do is my area divided by my channel's width. All right. So now that will give me, of course, if I have the channel's width, I have the depth of flow, I can actually find my method parameter. So my method parameter will be 18.5. Now, what if I said I want to have a different configuration of my dimension of my channel, but maintaining the same flow area? So if I use channels width of 1 meter, of course, my depth would be 4.5. That will give me the same flow area, which is 4.5. And my method parameter would be 10 meter, which is B plus 2y. That means it's 9 plus 1. I have 10 meter here. So this would be my, all right. This would be my variation of P. That means for what I've plotted here is my x dimension is the depth. My y-axis is the vector parameter, not dimensional axis is a vector parameter. So I have two, two plots here. All right. So if I were to increase my width, of course, my vector parameter will change as well. So I'm plotting this. So let's look at, for all varying channels width, what would I have? This would be the plot. Now you'll come to a point, right, which is here, about here, about when my depth of flow is 1.2, okay, and then sorry, that would be xy, okay. It should be, this is the depth of flow, okay, and then my water parameter, okay, would be somewhere 6.071, which is this one here. Okay, my depth is 1.2. Depth, this would be, actually this is the one, okay, which is the smallest one. Okay, so if you look at here, there'll come to a point where, at the varying channels width, okay, there'll come to a point where my wetted parameter is the most, is the minimum one lah, which in this case is 6 meter. When was it? When will it be P minimum is when my width is 3 and my Y is 1.5 meter. So this is how, this is the plot which shows that, with varying channels width and depth of flow, okay, you'll get varying wetted parameter. Now, in order to get the minimum wetted parameter, okay, of course, by mathematically we'll find, dp dy equals to 0. So you'll definitely get, at P minimum. So this will actually give you B equals to 3 meter and Y equals to 1.5 meter. That is what we are doing when we differentiate wetted parameter with respect of Y. We actually want to get this point here, all right, which will give us B 3 meter and 1.5, Y 1.5 meter, right? So we'll look at chapter 3 then, right? Okay. All right. You should be able to look at my slide already, can? Chapter 3?
Yes.
Okay, great. Thank you. Okay, now on chapter 3, today we are going to look at specific energy and control section. All right. Okay. This is just a overall what we have learned and what we are going to learn in our hydraulics. In chapter 1, January, we got to know everything, all right, in general. In chapter 2, we learn about uniform flow only, okay, where we use Chasey and Manning to find depth of flow. Why not? And now, of course, we also have, some knowledge on the best section, okay, of the channel. That is in chapter 2. So beginning chapter 3, we are going to learn about non-uniform flow in open channel. So this will be covered in chapter 3. So we are going to look at two cases which are flow over broad crested weir and also flow through constricted channel. that we are going to do analysis. We well okay, I'm going to explain later that the analysis that we are going to do in chapter 3 or this course here is actually simplification of the real situation. For example, I said go through constructed channel, right? In reality, right, the constructed channel could be, you know, you probably have obstruction on left and right of the channel. For example, go under a bridge, right? You have bridge piers, it is being constructed, or probably you have culvert under the road which constrict the flow. There are so many applications, but what we are going to learn is simplification of the analysis, but which we can apply. All right, the concept can be applied in real situation. Okay, for example, a flow over broad crested weir, we can actually use it to analyze when there's overflow over river dike, or also in rivers, right? Overflow, rocks and or weir or anything lah. All right, going through an obstruction. Okay, um, now, this is what we are going to learn in today's in chapter 3, today's lesson. Okay, chapter 3 is probably going to take between 2 to 3 weeks. Okay, and after chapter 3, we are going into, the same non-uniform flow under the same topic, non-uniform flow, but we are going into the difference between rapidly varied flow and gradually varied flow. So in rapidly varied flow, we'll look at one example, which is the hydraulic jump, okay, because it occurs very rapidly. And then for gradually varied flow, we are going to look at, backup of flow and also flow going through, overflow into a pond or anything lah. All right, there are a few examples of calculation in chapter 4. So I hope you are clear about the what we are going to learn in chapter 3. So we are going to learn about the concept of specific energy. Of course, as I told you earlier, there will be two examples that we are going to look at: flow over broad crested weir and flow through with constricted channel lah, basically. Okay, let's look at the concept of specific energy, which is introduced by Beckmetaf. Is the energy of flow measured with respect to channel's bottom. If you look at here, the total energy or specific energy here is the depth of flow y plus the kinetic flow v squared over the kinetic head, kinetic energy head, which is v squared over 2g. Now, there's no z or at bottom elevation, because it's measured from channel's bottom, so you don't need to plus that. This is specific energy, E, which is y plus v squared over 2g, so you don't need to add z 1 or Z2, it's actually measured from the channel's bottom. So I hope you are clear about this. If you still remember in your pipe flow analysis, right, you have Bernoulli's theorem, where you have, um, Y plus, I think you have pressure term, and you also have the velocity term there, all right? Okay. Your Y, I think you also have, your um, potential. Okay. Energy term there. All right. You have three terms lah, basically, in your pipe flow. Okay. Now, what is the use of specific concept or specific energy? It is used to define critical depth as well as to analyze lah, flow problems, which we are going to use later. Okay, in the subsequent slide, you'll see a few, quite a number of exercises lah. Okay, now for constant Q, remember, for a constant Q, that means Q does not change, is fixed. Your specific energy is given as y plus q squared over 2ga squared. Now, this you have this specific energy, which is E equals to y plus q squared over 2ga squared. Now, this expression of specific energy applies to all channel section. I can actually simplify this equation for rectangular channel. Okay, now for rectangular channel, I know that A, the flow area is equal to B times Y. Now, I also know that I can use discharge over unit width, which is discharge over V. Now, this expression here, I could actually simplify this for rectangular channel. Remember that rectangular section? I have here E equals to Y plus. Now, the numerator and denominator, I can actually simplify this. I divide the numerator and denominator with b squared. What would happen is q squared divided by b squared, I'll have q squared, the lowercase q squared, which is the discharge over unit width, and a squared divided by b squared, I'm going to have y. Y squared lah, basically. Okay, so this can be simplified as, sorry, y squared. Okay. So this, you can use this expression, all right, only for rectangular section. And sometimes, the question just give you discharge over unit width and then the depth. So you don't have to find the discharge. You don't have to find the flow area. So you can use this formula directly. All right. Okay, now let's look at the variation of E with Y, okay, which is represented by cubic parabola. Actually, what this graph tells you is actually, it actually describes this expression here. What would happen when Y changes? Q stay constant. Of course, when Y changes, your flow area will change as well. So what would, what would the variation E be? Okay, let's look at here. If your depth increases, right? Okay, if your depth increases, this would be the plot of your EY. That means this is actually the corresponding depth of flow. Okay, all right. So if this is corresponding depth of flow, you'll get, if you calculated, you try to find it, or you try to determine the specific energy, this is the point that you'll get, okay, with respect to the subsequent E lah, all right? So I have the plot here. Okay, now here's the thing, for a constant Q, imagine this, for a constant Q, a fixed slope, okay, just a second, someone is coming in. Okay, for a constant Q, a fixed slope, bed slope, or longitudinal slope. Okay, if the flow is very fast, let's say it's supercritical, right? It is fast flowing. That means the rate is very fast, the rate of flow is very high. You expect the depth of flow is thin, okay, because it's fast flowing, given a constant Q. Now, similarly, all right, if the velocity is low, that means it's in subcritical state. The depth of flow, you'll expect it to be thicker than the supercritical one because it's slow flowing, right? So the discharge is actually lower than the supercritical one. Okay, so this is why I show here. All right, if you look at here, I have critical depth of flow, but if the depth is smaller than this critical depth of flow, it is actually in supercritical state. Of course, you can show that the fruit number is greater than 1 lah in this case. Okay. And the depth of flow, if it's greater than YC, which is the depth of critical flow, this is in the state of subcritical flow. This is when fruit number is less than 1. Okay. So I hope you are clear. Okay. Because this is given constant Q. All right. Okay. Now, the next one, what I want to show is, okay, let me explain this chart here, this graph here. If you look at this dashed line here, this is actually, I wanted to show that this is actually the line of E equals to Y. Here's the thing, if you have your X and Y scale equal, you have equal scale, okay, that means this would be rectangular lah, okay, square, it will be square. Then this would be at 45 degree. This 45 degree actually depending on the scale of your E and Y. So it actually shows that if E is 1 meter, your Y would be 1 meter as well. So at this point, that would give you 45 degree. But if your scale is different, for example, if your E is, at every having the same square, your E is actually 2 meter and this is 1 meter. That means you are going to have larger than 45 degree lah, E equals to Y. But in this case, right, don't, 45 degree is just to show that I'm using the same scale for X and Y lah, axis. Now, I'm going to repeat this in bahasa. Sebenarnya garis dash yang warna merah ni menunjukkan nilai E sama dengan Y. Dan sebenarnya 45 darjah ni terjadi bila saya gunakan skala pada paksi X dan paksi Y sama. Maknanya bila pada satu senggatan tu ialah contohnya 1 meter, sini pun 1 meter. Maknanya saya akan dapat 45 darjah. Tapi kalau saya guna skala yang tak sama, contohnya satu senggatan kat sini saya guna 2 meter, sini 1 meter. Okay, saya akan dapat sudut yang lebih besar lah daripada 45 darjah. Saya masih boleh menggariskan garisan E sama dengan Y. Okey. Tapi bukan pada 45 darjah lah. Ini cuma nak bagi tahu sebenarnya jangan terikat sangatlah pada 45 darjah. Ini hanya berlaku kalau saya gunakan skala yang sama. Tapi the most important thing here is I want to inform you about E. What is the importance of having this E equals to Y? Now look at here. What does it shows when E equals to Y? It shows that this is 0. That means you don't have flow. That means you don't have Q. Can? So would it happen if it's you are analyzing, flow? That means, of course, you are going to have velocity, right? So therefore, what it shows here is, your E equals to Y curve, won't cross this E equals to Y. If it cross means your Q is 0. Okay, so it's actually going asymptote. Asymptote means berhampiran tapi takkan bersentuh lah pada garisan E sama dengan Y. So depending kalau E sama dengan Y you pada sudut yang berbeza, garis ni of course akan berhampiran dengan garisan E sama dengan Y jugalah. Itu maksudnya. That's why saya buat macam ni Y tambah, sebenarnya jarak ni ialah V squared over 2G. Okay, then you have your E1 here. Okay, the same thing here. This is your YC, alright? Because I'm using 45 degree, of course this height is actually YC lah, okay? Plus your VC squared over 2G, that means you are going to have your E mean, okay? It shows that there would be flow, okay? Because you have V squared over 2G. This would be the range of V squared over 2G. Okay, I hope you are clear about this graph here. Now, I wanted to show this in Excel. Okay, let's look at this Excel here. I'm going to enlarge this a bit. Let's see. Okay, I hope you are clear. Okay, now I hope you can see this clearly. Okay, now I have a fixed discharge. Let's use 20 Qmax. This is a rectangular channel, so I'm using a constant width, which is 2 meter. So what I'm going to show here is, as at varying depth pada ukur dalam aliran yang berbeza, okay, saya akan dapat specific energy ataupun tenaga tentu E yang berbeza. Jom kita tengok let's look at this. If my depth of flow is 0.5 meter, okay, of course, my area would be, B times Y. I'm going to have flow area. If you look at this formula, right, my B is constant. That's why I have the dollar sign there. I fix it, okay? Times my Y, I'll get A, all right? Okay, then my E would be, okay, look at this formula here. Okay, don't worry about this. I think, let's see. Okay, all right. Now, so my E, which is specific energy, would be Y. Y would be A6, Y plus, I have Q squared, which is, this Q is constant. That's why I lock it with dollar sign. I lock my column, I lock my row. Okay. This is actually, I'm locking it. So I have, 20 squared Q squared over 2 over G divided by 2 divided by G divided by A squared. This is my A, which is, say, 6. All right. I didn't lock A because as Y changes, my A changes as well. So it'll follow the different rows. So A squared. So this is actually my specific energy, which I have calculated to be 20.887 lah, or 20.89. All right. So I can actually reduce this to smaller. Okay. All right. Okay. To 5 significant number here lah. Okay, now let's see. Having the same Q, all right. So I said, let's look at what happened if the depth increases. So I have a 1 point here. Of course, just a second. Okay. Of course, the point of 20 here is not within this graph here, or within this limit here. 20 is actually way beyond 10. Because if I want to plot 20, all right, the graph will be very small. I actually want to enlarge this. That's why I plot until 10 meter only. So I have that. Okay, when the depth of flow is 1 meter, my flow area is 2 meter, then my specific energy is 6.097, which is here. All right. Now, what would happen if my depth is 1.5 meter? If my depth increases to 1.5, all right, my specific energy would be 2.765. All right. I can actually drag this. Okay. Now, then let's say if at every interval of 0.5 meter, I increase it at 0.5 meter. Let's look at what will happen next. All right. So you'll see that at every different depth, right, I have different specific energy. All right, different value of specific energy. It actually will overturn. Okay, so you are going to have a minimum specific energy value, all right, at a certain depth. If you look at here, this would be, it actually give me specific energy of 3.27 at depth of flow of 2.18 meter. Okay, if you look at here, all right, it actually, this area here will actually produce the minimum specific energy. So actually, now minimum specific energy is very important for the analysis. Later, you are going to see at the subsequent slide. Okay, that's why we need this. This is also when depth of flow is critical. Critical depth of flow will actually produce minimum specific energy. All right. So you'll find YC here and E min here. E minimum lah, E min here. Now, apart from E minimum, okay, at other specific energy, you actually would have two depth of flow. One would be in supercritical, the other one would be in subcritical state of flow. So what I'm saying here is, if you are solving this equation here, except for E minimum when Y equals to YC, for all other E, you are going to have two values of Y. One would be in subcritical state, the other Y value would be in supercritical state. Okay, I purposely wanted to show this because I wanted to show you that as Y increases, right, your E will come back at the same value, All right. So I hope you are clear with that explanation. All right, let's go back here. Now, this will actually explain this slide here. For a specific energy, specific energy, except for minimum specific energy, there are two depths of flow, Y1 and Y2. Now, this set of flow with having one specific energy is known as alternate depths. Okay. Sometimes the question would ask you, for a specific energy, find the alternate depths. That means you need to find Y1 and Y2 for a given specific energy. Now, if it involves energy loss, for example, in hydraulic jump, these alternate depths are known as sequent or conjugate depths. It's just the terminology that we are using is different. If it involves loss of energy, then it is known as conjugate or sequent depths lah. You'll come to this in reference book. You'll come to these terms. All right. So critical flow occurs when specific energy is minimum. So E min this would be the symbol for minimum specific energy with YC equals to critical depth. Now, you know that depth of flow is not possible, right? Negative depth of flow is not possible. You won't, because depth of flow is measured from the bed of your channel. So by right, the bottom of your channel is when Y equals to 0. So when there's flow, all right, of course, Y would be positive. It won't be negative, because this is not about groundwater flow, right? This is about open channel flow. So if you find, negative answer, that means you are going to have your answer will be wrong. Sorry, saya ada kelas. Kejap lagi saya call boleh tak? Okay. Hello? Saya ada kelas. Alright. Okay, sorry. I have to answer that because he's been calling me twice already. Okay. Now, let's just show when specific energy is minimum, okay, we can show that the Froude number is equal to 1. That means it's in the depth of flow, or the flow is in critical state of flow. So Y will be equal to YC. Okay, let's look at this here. Just a second. I'm going to change this. Okay. Now, so this is the expression of specific energy. When we differentiate, because we said E minimums occur when the depth of flow is critical, right? We are going to prove that. So when E minimums, that means we are going to differentiate dE E with respect of Y and set this equal to 0, then we'll get E minimum. So differentiating E with respect of Y, we are going to have 1 minus, we know that just now I have shown in the Excel, right? When Y changes, your A will change as well, right? So we are going to differentiate A. Q is constant, so we are going to differentiate A with respect of Y. You are going to have negative, all right, 3. That means you are differentiating A. Depending on, I cannot give, the formula of A here because it depends on the shape of your section. It could be rectangular, trapezoidal, or triangular, or any other compound shape. So differentiate A, you are going to get dA over dy. Okay, now at minimum specific energy, Y is equal to YC and A equals to AC. We are going to know that. Okay, so let's set dE over dy equals to 0. So this will become 0. Now here, dA over dy, I set it equals to TC. Now how do we come about that? You see, when we take an elemental, all right, of a section, of an element, this is a, this is, for example, you have earth channel, or natural channel. We are going to take the element of dA and dy. So dA would be, basically B times dy. You are going to get dA. All right. So this T here, all right, or B, if you look at here, B is also for this element, right? T is actually similar to B lah, basically. So T times dy will get dA. So therefore, dA over dy, I can use T to represent it. So therefore, you have TC. I set it equal to TC because I already set dE over dy equals to 0. So therefore, these are all, since I already recognize this as minimum, so this become critical state already lah. Okay, so therefore, rearranging this expression here, okay, I have this. Okay, now here's the thing. We know that, V is equal to Q divided by A. Okay, from the mass conservation, we know that Q is equal to AV, right? So V is equal to Q over A. So this, okay, Q squared over A squared, initially it was A to the cubic power, right? So this is actually A to the cubic power, but I'm going to change this to V squared, all right? Q squared over V squared, so I have V squared here. Okay, you know that D is equal to A over T, right? Okay, so this is the inverse of D. So I have the inverse of D here lah. Okay, so this actually is simplified to V squared over GD. V squared over GD equals to 1. So square root both sides. Of course, when you square root 1, it will become 1 as well lah. So square root both sides. Okay, since V squared, it will become V, and you have square root of GD. Remember, this is your fruit number formula. Okay, so it shows that, when the specific energy is minimum, all right, your fruit number is equal to 1. Therefore, the flow is in critical state. Okay, so you have proved that lah, basically. All right. Now, this is specifically for rectangular section. Okay, because we are actually trying to simplify things for rectangular section. Now, since Q is equal to Q over Q times B, I've explained this and how you come to this expression here. Basically, you both the numerator and denominator, you divide by b squared. So you are going to get this expression here. Okay, so rearranging this expression, okay, you just rearranging it, making discharge over unit width as the subject of the expression, then you are going to have this. So you can actually show if you plot Q with respect of Y, okay, um, when depth of flow changes, okay, you are going to get Q uh, in this curve, all right, in this parabolic curve as well. And when it is critical, okay, you are going to get Q max at critical depth of critical flow lah, basically. So this is how, you know, um, if you want to find, if you can find Q max, then basically you can find YC already. And if you know your YC, therefore you can find your Q maximum already. Okay, now let's see. Of course, in our case, our Q is still constant. Only that when B changes, your Q will change as well. The discharge over unit width will change as well. So you are going to get this curve lah, basically. Now for specific Q, all right, except for Q max, when it's critical flow, there would be two flow depths. Now remember here, we are using the conjugate depths term here because the one that we plot here, it is not related to energy already. There's no specific energy term here, all right, except for this lah, okay. Therefore, all right, we actually have two sets of depth of flow as well. So this is known as conjugate depths, okay. You are going to have subcritical and supercritical flow at any Q. All right, so you are going to have one set of depths. That means the conjugate depths. That means one is subcritical and the other one is in supercritical state of flow. Right? Okay. Now, critical flow occurs when discharge over unit width is maximum. That we have look at it. Okay, and then now it's the same thing here. All right, keeping E constant, assuming there's E is not changing. You are going to show, of course, you are not going to differentiate with E. That means E is not affected by depth of flow lah. Basically, you differentiate Q with respect of Y. Okay, so of course A, you have to differentiate dA over dy. So you differentiate this, and then again you are going to differentiate this term here. You are going to get this lah, basically. So this is uh, the multiplication of differentiation of multiplication values. So you are going to have this. So setting dq over dy equals to 0. This is actually you are going to get q maximum, because if you do second derivative, you are going to get this would be a minimum. Second derivative will be minimum, so you are going to get a maximum value. Sorry, negative lah. Okay, so you are going to get a maximum value of q. So setting it to 0, okay. So you are going to have rearranging lah. Basically, this equals to this, okay. And then you rearranging this expression here. You are going to get q squared t divided by g to the power a squared over a equals to 1. It's the same thing, This actually you set it equals to t, okay. You have t. Okay, this expression is actually similar to the one previously we had. So fruit number equals to 1. We can show as well in this case, all right? Now, state of flow, that's why in chapter 1 we learn about fruit number. So therefore, here you are seeing fruit number appears already. We are going to apply fruit number here. So critical flow occurs when fruit number equals to 1, when V equals to square root GD. Okay, that is when fruit equals to 1. Okay, it's critical flow. So Y is equal to YC. Fluid number less than 1 is subcritical. Your depth of flow is greater than YC, eh? Alright, if you look at this, okay, depth of flow will be greater than YC. This would be in subcritical, okay, in this case as well, okay. Subcritical depth of flow, if this is Y1, this is subcritical, is greater than YC. So supercritical, Y2 is less than YC. So supercritical, Y is less than YC and your fluid number is greater than 1 lah. Okay. Let's look at this activity 3.1 here. You have a rate of flow in a 3 meter wide rectangular channel is 10, given as 10 Qmax. Calculate specific energy if depth of flow is 3 meter and 1.2 meter. Now this is very direct. You just substitute in this specific energy equation. You have Q equals to 10. Okay. You have Y equals to 3 meter. Okay. You have, of course, A is B times Y, right? So you have B times Y, 3 times 3 lah, because since it's A squared, you have to square both, all right? So the specific energy is 3.063. Now, when the depth of flow is 1.2 meter, okay, you are going to have depth of flow of a specific energy of 1.593. Pay attention to this. Varying depth of flow. It doesn't necessarily means if depth of flow reduces, the specific energy will reduce. No, if you look at, this curve here, all right, this parabolic here, curve, not necessary. Look at here. When the depth of flow reduce small, okay, you have one specific energy. When it increase, you are going to get the same specific energy as well. So not necessary when the depth of flow increase, you are going to get increase in specific energy. No. All right. This is just this exercise is used for you to apply the specific energy equation only. Yeah. Now for activity 3.2, right? Okay. It asks us to calculate specific energy for a, look at this unit. This is actually discharge over unit width, which is the lowercase q, not the uppercase q. All right. In a 1.6 meter wide rectangular channel. So when normally if discharge over unit width is given, I know it normally will involve rectangular channel lah. Okay, the depth of flow is 0.65 meter. What are the alternate depths for the flow? That means you need to find Y1 and Y2, Y1 and Y2 for specific E. Okay. We need to find E first lah, basically. Then after that, you need to justify state of flow for each depth. You need to find what is the state of flow for Y1 and Y2. Definitely one would be in subcritical and one would be super. I don't know which one. Now, normally, the larger depth would be in subcritical and the smaller depth is in supercritical flow. That you know, all right? So let's look at this exercise here. Okay, so I'm going to switch this. Okay, we are going to have this reduce. I have the answer already over there, right? But it's okay. Okay. All right then. So in this activity 3.2 here, all right? So I have a rectangular channel. So the first thing, as I told you earlier, is I need to find my specific energy for this problem here. So I have E equals to Y plus, the formula that I'm using is this one, because discharge over unit width is given, so I might as well use this. I don't have to calculate for discharge anymore. So I have, oh sorry, Y squared, okay? So I have that. Okay, so I'm going to substitute the values provided. The depth of flow is 0.65 meter. My discharge will be 1.2. Discharge over unit width. So this would be, this is 0.65 squared. Okay. Now, this will give me specific energy of, could someone help me calculate this, please? Can I have dial? I think I have a my student called how do you pronounce your name?
That
Dial.
was
Okay. Could you help me calculate this?
yeah.
Okay. Oh, I thought you are okay. Your name, I thought you are a girl. Okay. It's
0.82
very nice name. 0 point
0.824.
824. Okay. 824. Okay. I could also give the fourth significant number, which is 8237. Okay. Now, yeah. All right. Thank you. So I have those. Then the next thing I want to find would be, okay. Here's the thing. I know that. Okay. I want to find these two depths, okay, at given specific energy, which is 0.8237. So the next thing I want to do would be, okay, I need to solve for this depths of flow. Now, here's the thing, look at this. Using the same expression here, okay, I know that, okay, the same specific energy, here's the thing. I already have 0.65 meter. I don't know which one. Either here or this. I don't know. But actually, I could check whether it's subcritical or supercritical. Okay. But I need, having the same specific energy, there would be another answer or another set of, another value of depth of flow for me. Okay. But the thing that maybe I want to do is I can check whether this is the supercritical or the subcritical depth of flow. So what I can do is, since the question also asked me to check to determine the state of flow, right, using Freud number, I can find the Freud number for this lah, basically. So now, whether it's subcritical or supercritical flow, how should I distinguish it is I probably need to find YC first. Okay, depth of flow, sorry, critical depth of flow. YC would be Q squared over G 1 over 3. Okay, later I'm going to show you how you get to this equation here. Okay, don't worry about this. Okay, so this would be so YC actually is 0.5275 meter. Now comparing this depth with this depth, okay, so you have a depth of 0.65 meter. Can Kang Pao, are you there?
Yes, doctor.
Okay, may I know, at this depth here, Is it supercritical or subcritical state of flow given this step? This is YC, which is 0.52.
Subcritical.
Subcritical. So it's here, thank you. This is subcritical. Let's put it as Y2 lah. Because it is greater than YC, therefore it's subcritical. It's critical, okay. Now, therefore, you are going to expect the other alternate depth would be in supercritical, which should be smaller than 0.53. If you look at this graph here, so what we need to do is we are going to solve the same expression, okay? This time, okay, I have the same expression. I'm rewriting it. I'm organizing it, rearranging it. Solving this, 1.2 squared divided by 2 divided by 9.81, I'm going to get okay, can you help me find the another depth? Another alternate depth using this expression? Can all of you try? This is also the try and error. You need to use the try and error method when you need to solve it using the calculator. You have to, write this expression in your calculator and solve it. Can you do that for me, please? What would be Y1? Bear in mind, when you solve the first time, you probably will get 0.65. I think you need to solve the second time, or probably the first time already you get this answer. Actually, the answer is on my slide already, but you have to try it out. I'm not sure whether the answer is correct or not. How come I get another answer? But help me check whether it's correct or not.
Doctor.
Yes.
From the top, you write the Q is equal to 1.2, so you get a different value.
Oh, I'm sorry. This one.
Top again. From the
Here.
top. Yeah,
This one. Okay.
it's 1.23, but you write 1.2.
Oh, it should be 1.23, is it? Okay. All right. This is 1.23 lah, basically. How about this value here? This will change as well. Am I right?
Yes,
Okay. What is the right one?
0.8325.
Okay, great. So, okay, this would be 1.23. Okay, I think when I calculate it, I use 1.2. Okay, so knowing this is 0.8325, okay, therefore, can you help me recalculate the depth of critical flow?
Zero 0.5363. Sama tak?
Anyone can help confirm it?
Yes, same.
Yes, correct.
Same.
Correct, doctor, correct.
Same, eh? Okay,
Correct.
thank you. Okay, now that's why it's good to have you help me check my answer. So therefore, I need to change this as 1.23 and this should be 0.8325. So how about this? Can someone help me calculate this? Can someone help me calculate 1.23 squared divided by 2 divided by 9.81?
1.5129.
Are you sure? Because it's quite
Saya dapat
far.
0.07.
0.0771.
Yes.
One.
0.07.
0.07711.
Okay. 7711. Okay.
7711.
Okay, thanks. Thank you. All right. So using this, okay, cross this out using 0.07711 and this would be 0.83. I'm going to rewrite this. This is a mess, right? So okay, can you help me find y1? You should get around 0.4 something.
0.4476.
How come your voice is so slow? You're afraid, is it? Confident, alright? Okay, anyone want to help, give confidence to our friend here? Again, since you found it to be 0.4476, right? You can actually substitute it again in this expression and then check. If it gives you 0.8325, then this would be correct lah. Okay, you can substitute 0.4476 plus this term divided by 0.4476 squared. You should get this back.
Dapat sama.
Sama ya? Okay, so now this would be the depth in, of course, it asks you to find fruit number, right? You need to show it. So based on fruit number. Oh, I think earlier also you need to find fruit number. It doesn't matter what you can do is you have conjugate depths. Y1 equals to 0.4476 meter and then Y2 is 0.65 meter. You can actually find fruit number. Okay, so since you don't have velocity, right, what you can do is for each of these, okay, You can get this, right? This is actually this, eh? Let me show this to you, okay? Fruit is equal to G square root. You know that fruit is equal to square root GD, right? The original formula, correct? So for rectangular, okay, for rectangular channel, specifically rectangular section, D is equal to A over T, BY over B. So for rectangular section, you have showed that D is equal to Y. The hydraulic depth is equal to Y. So therefore, right, fruit is V over square root GY. Okay, one is that. Then you also know that, okay, you know that Q is equal to AV. Okay, divided by, since it's rectangular also, okay, you divide it by B both sides, you are going to get, okay. So therefore, rearranging this, you are going to have Q over Y. Clear so far? So therefore, okay, when I said, you know, you have fruit equals to this term here. So I'm substituting velocity with Q over Y. Then I combine this into here because Y is also equal to square root of Y squared, right? It's actually Y, right? So I combine it in the square root. I'm going to have Y to the cubic power. So therefore, okay, I actually have this guy here. All right, it's the same. Okay, so you have your Q of 1.23. This you need to help me calculate because I'm using 1.2. Another set would be this. I'm using fruit 1. Then the depth of 2 would be help me calculate this first. Okay, this is cubic power. This is cubic power as well. Can anyone give me the answer, please?
If
1.311.
This one 1.311.
Yeah.
Okay, thank you. No unit, right? So this is greater than 1. This is supercritical. Correct or not?
Correct.
Then this one?
0.749.
490, is it?
3. 4.
93. Huh? 4. Okay, thank you. This is less than 1. So it's subcritical. Okay, so that's it. You have already solved this. Okay, so therefore, okay, luckily you helped me correct this answer for me. So this is, I need to, recalculate this. Okay, so therefore, okay, I want help from one of you to solve this next week for next class. Which is you need to show your solution on Wednesday. The person that I have chosen would be, where's the name list? Okay. I have here Kevin, right? Kevin, are you here?
Yes, doctor.
Okay, this is your task for next for the coming Wednesday. Then oh, okay, this one I can actually show you a quick one lah, basically. Okay, remember just now I'm using this formula here. Okay, now let's show this. Okay, I'm going to show this. Okay. Okay, let's look at this. I'm going to rearrange this into, okay, I'll bring A and TC because A and TC is actually is the function of Y lah, basically. I have here. Okay, therefore, all right. Now, for rectangular channel, remember actually this formula that we are using here. Where is it? Okay, this formula here. It actually applies only for rectangular channel. So we are going to look at how we are going to simplify this formula here. Okay. For rectangular section, okay, this would be B cubic YC cubic over B cubic equals to Q squared over G. All right. So of course, okay, it doesn't matter. So I can have this, okay. Sorry, this is not cubic, okay. So this become, this become 2, all right. So I have that, okay. Now y c cubic. So this one is cancelled already with this. I have b squared here. Let's do it slower, okay. So yc cubic is equal to q squared over b squared g. All right. This one here is q squared. All right. So yc q squared over g. All right. So therefore, you can show that this is q squared over g. Or normally, I can write this in terms of this guy here. All right. So for rectangular section, okay, you can simplify this formula here. All right. Okay. Now I have asked Kevin to help with this. This is a bit difficult. Maybe not so. But the solution is provided already. Maybe I want to ask for 3.5, right? For 3.5, have I given the solution to you in your notes for 3.5? Have I? Anyone? Do you have the solution for 3.5 in your notes?
No.
No, Okay, if no, then can I ask Fatin or Aina to help me find critical depth? Fatin, are you there?
Yes.
Okay, that is your task, Okay.
Okay.
And then can I have Abu Hafizuddin? Abu, are you there?
Yes.
Okay, help me solve for B, critical velocity. And then can I have Fauzan? Fauzan, are you there? Fauzan? Fauzan? Missing in action? Okay, if Fauzan is not there, can I have Mafira? No, Mafira.
Yeah.
Okay, help me solve critical slope. Now I know that I haven't teach some of some of the formula maybe that you should be using in solving activity 3.5. You can go through the slide first. If you have problem, you can of course WhatsApp me lah to check whether you are doing the right thing before presenting. Okay, clear? Clear, guys. You guys are clear?
Clear.
Okay, if you are clear, then I'm going to end the class for today. Yes, Kampao.
Sorry, doctor.
Yes,
For the calculation of section factor just now, for the
yes.
equation, if I get an x for a different answer, just now because we get the answer 0.4 something, right? But now I get 0.6 something, but end up when I substitute the value I get into the equation before, but I get the same answer.
Okay, you are saying just now the activity 3.2, am I right?
Yes.
Okay, you know what, Kampao, I'm going to recalculate and then I'm going to share the answer in our group. Is it okay?
Okay.
So because just now a couple of us are having the same answer, so I wasn't sure whether your answer, your friend's answer or my answer is correct. So what I'm going to do is I'm going to recalculate and then I'm going to share it. So we can reconfirm the answer lah in the group later. Okay,
Okay.
eh?
Sure.
Alright. Okay, thank you, Kampao.
Doctor,
Yes,
for
Johnson.
the test one,
Yes.
which chapter include?
Chapter 1, 2, and 3.
The whole chapter 3.
No. Normally up to what you have learned only. Don't worry.
Okay. Thank you.
Don't worry. Okay. Don't worry. I'll tell you. When was this schedule? I can't remember.
Next Sunday.
Oh, next Sunday. Oh, don't worry. I'm going to guide you for your test lah. Don't worry. Okay. Okay. Anything else? Taba?
Actually, I want to ask the 3.2, the last answer, the fruit number 1, but it's okay. Since doctor want to recalculate, right?
Yep.
So okay, I'll just wait. Okay.
All right. Okay. I may
Because I
have
get
to
different
give
answer
you.
too.
I may have to share the answer later in the evening because I have already scheduled things to do afterwards, so I probably have to share a bit later. Sorry about that, to all of you. All right. Okay. Anything else? All right. Ada apa-apa lagi tak untuk kelas hari ni? Kalau tak ada, I'm going to see you on Wednesday. All right.
Okay, doctor.
All right. I'll see you guys. Bye-bye. Bye.
Thank you, doctor.
Thank you.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.
Bye-bye.
Thank you, doctor.
Thank you, doctor.
Bye.
Attendance.
Thank you, doctor.
Oh, attendance, I'm going to share again. Oh, I think in your group, someone share in the WhatsApp group, eh?
Right. No, it deleted already.
Huh? Oh, deleted already. Okay.
Yeah, deleted. Okay, thank you, doctor.
Okay, thank you, Ahmad Aizat.
Give it.
All right.
Thank you, doctor.
Thank you. Faisal, Priya, are you there? I'm going to end the session already, eh?
Yeah, I'm
All right.